On the morning of November 12, something unexpected happened above the thin red horizon of Mars. China's Tianwen-1 orbiter, which has spent years circling the planet in near silence, turned its high-resolution cameras toward a point of light moving against the background stars. What it recorded over the next several minutes did not match any model in the mission's internal catalogue. The object was small, compact, and strangely stable. No dust fan, no coma, no tail, just a sharp reflective point that seemed to pulse, as if responding to the sunlight sweeping across its surface. At first, engineers assumed it was a passing asteroid. Then the orbital path was checked. The numbers were exact. This was 3I Atlas. The interstellar visitor that had already challenged telescopes on Earth was now visible from Mars. And Tianwen-1's perspective revealed something scientists had quietly feared for months. The object was changing in a way that only became obvious when viewed from another planet. If these developments keep you as focused as they keep me, make sure you like this video and subscribe so you never miss an update. Tell me where you're watching from and the exact time there. And if you want to help this community grow, share this video wherever you can. Every view helps us track one of the most mysterious visitors our solar system has seen. Now let's walk through Tianwen-1's images and the 22 scientific chapters that explain why this moment matters. When Tianwen-1 captured 3I Atlas on the morning of November the 12th, what made the images so valuable was not just the object itself, but the exact geometry under which the encounter happened. In astronomy, geometry decides everything. It determines how light scatters, how shadows form, how much truth a camera can extract from a body that should be little more than a moving point of light. And in this case, the alignment between Mars, Tianwen-1, the Sun, and 3I Atlas created one of the cleanest and rarest vantage points we have had since this interstellar visitor entered the inner solar system. At the moment of the observation, Tianwen-1 was positioned on the day side of Mars, but in a region where the local illumination was soft rather than harsh. The sun was low relative to the spacecraft's line of sight. That meant sunlight was sweeping across the surface of 3I Atlas at a shallow grazing angle. This grazing illumination is a powerful tool in astronomy. It exaggerates small surface features, enhances microshadows, and reveals changes in brightness that would otherwise be invisible under direct overhead lighting. Earth telescopes never saw 3I Atlas under this configuration, because from our perspective the object stayed closer to the sun's glare. Mars provided a clean stage where the lighting conditions were fundamentally different. The second geometric factor was distance and background. Tianwen-1 saw 3I Atlas from a side angle that placed the object against the soft red glow of Mars' limb. That glow, created by scattered sunlight in the thin Martian atmosphere, acted like a natural backlight. Instead of blending into deep black space, 3I Atlas was set against a gradient background. Backlighting is useful because it reveals even faint dust or gas structures if they exist. A single reflective grain can stand out if the background is bright enough. But in the Tianwen-1 frames, nothing appeared. No tail, no halo, no dust filament. The object remained a hard, sharp point, unaffected by the lighting conditions that should have exposed any surrounding material. A third element was the viewing angle relative to the solar wind. From Mars, Tianwen-1 was looking at 3I Atlas, from just off the solar wind's direct flow line. This means the orbiter saw both the sunlit face and part of the forward-moving side simultaneously. If dust or ionized gas had been streaming off the nucleus, the geometry should have revealed an asymmetry. Instead, the brightness stayed symmetrical with only a faint forward enhancement, something more consistent with a reflective or hardened surface than an active venting comet. The final piece of the alignment was the orbital placement of Mars itself. Mars was behind Earth in its orbit, creating a longer baseline for parallax. By combining Earth's ground-based coordinates with Tianwen-1's images, scientists gained a stereo-style depth measurement. That depth confirmed slight non-gravitational motion. The object was shifting in a direction not fully aligned with its predicted gravitational path. This shift matched earlier readings from Earth, but was more pronounced because the viewing baseline between Earth and Mars provided a wider geometric spread. All of this means the alignment on November 12 was not accidental. It was the product of orbital timing, spacecraft positioning, and natural lighting physics converging in a narrow window. The geometry cut through noise that normally obscures faint structures. It gave scientists a second angle to measure motion. It revealed a reflective behavior that comets rarely show. And it confirmed the absence of features that should have appeared if 3I Atlas were behaving like a typical volatile-rich interstellar comet. The alignment did not just allow Tianwen-1 to see 3I Atlas, it allowed the geometry itself to tell a story of an object that remains sharper, cleaner, and more resistant to solar influence than any comet we have documented this close to the Sun. When Tianwen-1 examined 3I Atlas on the morning of November the 12th, one detail stood out immediately in the raw frames. The object appeared as a perfectly sharp point of light, not softened, not surrounded by the faint haze expected from even the weakest comet activity. Instead, the source was crisp, almost star-like, with a clean boundary that did not blur or stretch across exposures. For scientists familiar with comet imaging, this was the most unexplainable part of the entire sequence. To understand why this matters, it helps to look at how comets normally behave when seen through high-resolution instruments. Even at great distances, sublimation produces a subtle glow around the nucleus. Dust reflects sunlight. Gas molecules scatter it. The result is a fuzzy envelope known as a coma. The coma can be extremely faint, but it is almost always present because comets release material continuously when warmed by the sun. The boundaries of the nucleus blur into the surrounding haze, giving the object a soft appearance rather than a pinpoint signature. Tianwen-1 did not record anything resembling that. Instead, 3I Atlas looked more like a stellar point measured through a stable atmosphere. The edges did not expand with longer exposures. There was no blooming of light on the sensor. The spacecraft's imaging system is sensitive enough to detect faint particulates around Martian dust storms. If even a small coma existed around 3I Atlas, the camera would have captured at least a trace of it. The absence points toward a complete lack of visible outflow, which is rare for any comet this close to the Sun. Another important detail was the photometric stability of the point. Comets often show small fluctuations in brightness as their jets rotate and release uneven amounts of material. These fluctuations create short-term flickers that appear as micro-variations between frames. Tianwen-1 observed mild modulation, but not the chaotic fluctuations associated with surface venting. The stability suggested a body with a uniform reflective face, or a surface capable of scattering sunlight more evenly than the porous layers seen in typical comet nuclei. The sharpness also revealed something about the object's physical structure. If 3I Atlas was shedding dust, the immediate area around the nucleus would contain particles reflecting varying amounts of sunlight. This produces a gradient of brightness extending outward. Instead, the light profile around the nucleus dropped off steeply. The transition between the object and the surrounding darkness was sudden. This implies that the material around the object is either non-existent or extremely sparse. In other words, whatever is happening internally is not breaking the surface in a way we can detect. A secondary explanation could involve particle size. If 3I Atlas were ejecting ultrafine dust, the particles might scatter light poorly and remain invisible, but such dust would still broaden the point spread function of the image. Even the smallest grains affect the halo structure around a light source. Tianwen-1's data did not show this. The nucleus remained compact and untouched by any detectable haze. This argues against fine dust and supports the idea that outgassing is minimal or absent. Another angle comes from the lighting geometry. The Sun was positioned at a grazing angle, which usually enhances the visibility of tenuous features. Dust near a comet tends to brighten under shallow illumination. That enhancement never appeared in the Tianwen-1 frames. The side lighting should have revealed even the faintest ejecta, but the frames remained identical across exposures. The sharpness held steady under different lighting weights, suggesting the lack of outflow was not an imaging illusion. This sharp profile matches earlier ground-based observations, but Tianwen-1's images carry more significance because they were taken from a different planet, with a different atmospheric environment. Earth telescopes must fight atmospheric distortion. Even adaptive optics cannot fully eliminate softening. The Martian vantage point removed that limitation. What Tianwen-1 delivered was a raw, clean look at an object near the Sun without the atmospheric scatter that normally dilutes fine details. So the conclusion is simple but profound. 3I Atlas behaved as a point source when it should not have. The sharpness of its appearance contradicts the physics of volatile rich bodies heated by solar radiation. No coma, no haze, no hint of the material expected to surround a typical comet. The nucleus acted like a compact reflective object instead of an active interstellar comet approaching perihelion. When scientists reviewed Tianwen-1's images of 3I Atlas from the morning of November 12, one detail immediately challenged conventional expectations. The object showed a faint but measurable brightening on the forward side of its motion, the region facing into the solar wind. In comet science, this should not happen. Forward brightening is rare, and when it does occur, it usually requires a dense dust environment that scatters sunlight at shallow angles. But 3I Atlas does not appear to have a dust environment at all, which makes the observation stand out as one of the most unusual features recorded by the orbiter. Under normal conditions, a comet becomes brightest on the side facing the Sun. Sublimation releases gas and dust, which scatter sunlight efficiently. Because most of this material flows away from the Sun, the illuminated region generally forms on the trailing side of the nucleus. The forward face, the leading edge of the comet as it moves through the solar wind, typically remains dimmer. Dust grains on that side are quickly swept back by radiation pressure and charged particle flow. Even for interstellar comets, which may have different compositions, this behavior usually holds. Forward brightening is therefore a sign that something unusual is interacting with sunlight on the object's nose. In the Tianwen-1 frames, the brightening appeared as a soft gradient rather than a sharp spike. It was subtle but consistent. Frame-to-frame comparisons confirmed it was not noise or camera scatter. The bright region stayed anchored to the direction of motion, not to the direction of sunlight. That distinction matters. If the effect followed sunlight, it would be ordinary phase illumination. Because it followed the trajectory vector instead, it suggests either a reflective phenomenon or a structural characteristic of the surface facing the solar wind. One explanation involves surface texture. If the front side of 3I Atlas contains smoother or more coherent material than the rest of the nucleus, it may reflect sunlight more efficiently. Smooth surfaces can produce strong forward scattering effects under certain angles. But this explanation requires a degree of uniformity not typical in comet nuclei, which tend to be chaotic mixtures of dust, cracks, and porous surfaces. A smooth reflective plate-like region would be unusual but not impossible, especially for an interstellar object shaped by cosmic radiation over long timescales. Another possibility involves micrograins embedded on the surface. Some silicate particles scatter light strongly when illuminated from behind. If the forward face contains a layer of such particles, they could create the faint glow Tianwen-1 observed. But again, this assumes the presence of dust or particulate material that should have been detected elsewhere around the nucleus. So far, no readings from Mars or Earth have shown evidence of a dust coma, which makes this explanation harder to support. A third interpretation is dynamical. When an object moves rapidly through the solar wind, the charged particles can interact with its surface in ways that create slight localized heating or changes in reflectivity. Although not bright enough to produce visible emission, this interaction could alter how sunlight bounces off the leading side. If 3I Atlas has a conductive surface layer, even one only a few millimeters thick, the solar wind could be intensifying the scattering pattern on the nose of the object. That would produce the exact type of forward-facing brightening Tianwen-1 recorded. The most interesting detail is how stable the brightening appears across exposures. It does not flicker or shift noticeably. That stability implies that the feature is structural rather than temporary. Comets undergoing sublimation often show fluctuating jets that change brightness quickly. Here, the forward glow stayed almost identical across the observation sequence, suggesting that it is not tied to short-term activity. Instead, it may be a property of the object's surface or its interaction with solar wind flow. Forward brightening also has implications for the object's rotation. If 3I Atlas was spinning rapidly, different regions of the nucleus would face forward at different times. The brightening would move or fade. Tianwen-1 did not observe such changes. This hints at either slow rotation or a stable orientation during the observation window. Both scenarios add weight to the idea that the forward-facing sector has unique physical characteristics. In the end, the unexpected forward brightening adds another layer to the growing mystery. It is not strong enough to indicate activity. It is not chaotic enough to indicate dust release. It is subtle, persistent, and directional, and it appears on an object already known for violating the standard rules of comet behavior. When Tianwen-1 captured 3 Atlas on the morning of November 12, it did so under lighting conditions that few spacecraft have ever experienced. Mars was positioned in such a way that the planet itself acted as a giant natural backlight. This created one of the clearest observational stages we've had in the entire 3I Atlas timeline. What made these images so compelling was not only what they showed, but what they failed to reveal. Against the soft red glow of Mars, 3I Atlas appeared as a clean, compact point, with none of the extended structures that would normally betray a comet under solar heating. Mars is an unusual backlight because its atmosphere is thin, but not thin enough to be invisible. Dust suspended in the lower atmosphere scatters sunlight into a reddish gradient that rises above the horizon. When Tianwen-1 looked outward from orbit, this glow created a bright backdrop against which even faint particulates would stand out. If 3I Atlas had been shedding dust, the backscatter from Mars would have highlighted the grains as pale streaks or diffuse wisps. Nothing appeared. The image remained perfectly clean. This effect works similarly to twilight photography on Earth. A soft gradient behind a subject enhances the visibility of any fine structures. Astronomers often use twilight skies to detect faint aerosols or thin atmospheric layers. Tianwen-1 found itself in a natural version of the same setup. Mars provided the glow, space provided the darkness. 3I Atlas passed through the middle, like a silhouette carved against the horizon, and yet nothing about its structure behaved like a silhouette of an active comet. The object's boundaries remained sharp and continuous, without any haze bleeding outward. Another reason this backlight was so important is the angle at which the sunlight reflected off Mars. The sun was positioned low relative to the Martian surface, producing a gentle uplight effect. This meant the lower region of the sky was brighter than the upper region, which amplified the contrast around 3I Atlas. Any tail, coma, or dust plume rising above the nucleus should have been illuminated from below. That type of underlighting normally exaggerates scattering and makes even faint emissions visible. The absence of such emissions reinforced the finding that the object had no detectable coma at all during the observation window. The Martian backlight also provided key information about the object's motion. When the background behind a moving object contains a gradient rather than uniform darkness, scientists can detect microshifts more precisely. The subtle change in contrast around the object's edges allowed analysts to measure slight displacements in its position across frames. These displacements hinted at non-gravitational acceleration. The effect was small, but the backlight made it easier to measure than if Tianwen-1 had observed the object against deep space alone. Another benefit of the backlighting was the suppression of sensor noise. Spacecraft cameras can produce faint background artifacts in low-light conditions, but when the field of view contains a smooth gradient, those noise patterns are reduced because the sensor is not working at full amplification. The resulting images of 3I Atlas were unusually clean. The clarity removed one of the most common excuses for missing faint comas: noise contamination. Here, the environment eliminated that uncertainty. If a coma existed, the camera would have registered it. Backlighting also provided insight into the temperature distribution around the object. Dust normally glows faintly when heated by sunlight, especially near Mars' orbital distance. The glow can be subtle, but when positioned in front of a softly lit background, it can become detectable through slight shifts in color or brightness. Tianwen-1's instruments found no such variations. The surface around 3I Atlas remained uniform. This suggests that there were no dust grains absorbing and re-emitting solar energy, reinforcing the idea that the object is not releasing the kind of particulate material associated with a volatile-rich comet. In the end, Mars acted like a cosmic spotlight aimed not at illuminating the object, but at exposing the absence of expected features. The planet's soft glow turned into a scientific tool. It enhanced contrast, it revealed structure, it confirmed stability, and most importantly, it proved that 3I Atlas was travelling through the inner solar system without producing the visible outflow that every comet this close to the Sun should show. Seen against Mars, the object behaved like a compact, stable body, not a fragmenting or venting comet. The backlight turned a routine observation into a rare, revealing moment in the study of this interstellar visitor. One of the most revealing aspects of Tianwen-1's November 12 observation of 3I Atlas was not the object's brightness, nor its stability, nor even its razor-sharp appearance. It was the motion, a motion that should not exist without an accompanying physical mechanism. In the high-resolution frames captured by the orbiter, 3i Atlas displayed a slight but measurable shift in its position across time. This shift, small enough to appear insignificant at first glance, carries weight because it points to non-gravitational acceleration, and yet nothing in the images shows the outflow required to create such acceleration. This contradiction sits at the heart of one of the most persistent mysteries surrounding 3i Atlas. In celestial mechanics, non-gravitational acceleration is well understood. When an object expels material, even in small amounts, it produces a recoil force. Comets often behave like weak rockets. Gas escapes through surface vents, sunlight heats pockets of volatile ice, and dust streams away from the nucleus. These effects add up to tiny thrusts that slightly alter the comet's path. From Earth, these shifts are hard to detect, but with sensitive enough instruments, scientists can measure the subtle drift. The direction of the drift often matches the distribution of the outgassing jets. In the case of 3i Atlas, Earth-based telescopes had already reported irregular position offsets, suggesting that something was pushing the object in ways gravity alone could not explain. But atmospheric distortion and geometric limitations made those readings difficult to interpret. Tianwen-1 provided the missing piece. By observing the object from a second planetary position, analysts gained a triangulated view of its motion. The parallax between Earth and Mars was enough to confirm that the object's trajectory contained a slight outbound deviation, a deviation consistent with a thrust-like effect. The problem is simple: thrust requires mass loss. But Tianwen-1 detected no mass loss at all, no jets, no plumes, no haze, no dust trail. The object looked inert, not active. It resembled a reflective point of light rather than a body undergoing sublimation. If gas were venting from beneath the surface, the backlit glow from Mars should have illuminated the outflow. The camera should have picked up even the smallest plume. Instead, the space around 3i Atlas remained empty. This leaves scientists with a narrow set of possibilities. The first is that the outflow exists but is invisible due to the properties of the material. Extremely fine, ultra-dark particles could escape detection if they scatter light poorly. Certain carbon-rich grains can behave this way. However, even the faintest scattering usually appears under the grazing illumination that Tianwen-1 experienced, especially when a bright planetary backdrop is present. The lack of detection weakens this explanation. A second possibility is that 3i Atlas is expelling gas without dust. Pure gas outflow would be harder to see visually, especially if it expands quickly. But even gas should create a slight halo, since ionized molecules fluoresce under solar radiation. Tianwen-1's instruments did not register any extended glow. The profile around the nucleus dropped off steeply, suggesting the absence of gas emissions. A third possibility involves geometry. It is conceivable that the outflow is occurring in a direction opposite the spacecraft's line of sight, effectively hiding it. But Tianwen-1's angle relative to the object was wide enough that any outflow substantial enough to alter the trajectory should have been partially visible. The fact that it was not indicates that if outflow exists, it is either extremely narrow, precisely aligned away from both Earth and Mars, or weaker than required to explain the measured acceleration. The final possibility challenges the traditional comet model. If the acceleration is real and not produced by outgassing, then some internal or external mechanism must be responsible. This does not imply anything artificial. Natural bodies can sometimes produce asymmetric forces due to thermal stress, crack propagation, or momentum redistribution inside fractured layers. But these scenarios are rare and usually accompanied by visible structural changes. 3i Atlas showed none. In the end, the Tianwen-1 observations highlight a clear contradiction. The object is moving as if something is pushing it, yet the space around it remains silent and empty. Motion without visible outflow. A phenomenon that forces scientists to reconsider whether 3i Atlas is behaving like a comet at all, or whether it belongs to a class of interstellar objects that do not follow the rules we have learned from our own solar system. When Tianwen-1's raw frames were first reviewed by analysts on the morning of November the 12th, one feature immediately drew attention. For a brief moment, lasting less than a second in the sequence, 3i Atlas produced a sudden increase in brightness. It was not dramatic or explosive, it was subtle. A clean, sharp pulse of light reflected directly toward the orbiter. This brief spike, though short-lived, became one of the most important clues in understanding the physical nature of the object. Reflectivity spikes occur when sunlight hits a surface at the exact angle required for a specular reflection. Most comet nuclei do not produce such spikes. Their surfaces are rough, porous, and irregular. They scatter sunlight diffusely, creating soft glows rather than sharp flashes. To generate a narrow directional spike, the reflecting surface must be smoother or more coherent than the fractured, dusty terrain that defines typical cometary bodies. The spike Tianwen-1 recorded suggests that at least part of 3I Atlas possesses a surface texture unusually capable of reflecting sunlight with precision. The first question scientists asked was whether the spike came from dust. Loose particles can sometimes flash when they catch sunlight at just the right orientation, but this explanation does not fit the data. Dust flashes are usually followed by a brief halo or a faint streak as the particles drift away. Tianwen-1 saw none. The space around the object remained clean. The spike originated from the nucleus itself, not from material floating nearby. Another possibility is rotational glint. If 3I Atlas is rotating slowly and possesses one region that is smoother or more reflective than the surrounding surface, that region could momentarily direct a beam of sunlight toward Tianwen-1. This would create a short-lived brightening, but such a glint usually appears periodically if the rotation is steady. Analysts reviewed the surrounding frames for repetition. No second spike appeared. The event was singular. This suggests that either the rotation period is long enough that only one reflective moment occurred during the observation window, or the surface responsible for the reflection is positioned in a way that makes the alignment extremely rare. The spike also provides information about the object's reflectance ratio. By comparing the brightness increase to the baseline luminosity of the nucleus, researchers inferred that the reflecting surface must be significantly more efficient at scattering sunlight than the surrounding material. This difference implies surface heterogeneity. Most comet nuclei show heterogeneity, but in the form of volatile patches, dark organic crust, or fractured planes. They do not typically include areas capable of producing specular reflections. The spike therefore stands out as evidence that 3I Atlas contains material unlike the usual mix of ices and dust. The geometry of the event is equally important. Tianwen-1 observed the spike at a moment when the sun was positioned low relative to both the spacecraft and the object. Grays-angle illumination usually emphasizes roughness, not smoothness. Rough surfaces cast shadows and create soft gradients. Only smooth surfaces remain bright under such lighting. The fact that the spike appeared under these conditions reinforces the idea that the reflecting structure has a flat or polished quality relative to the rest of the nucleus. The absence of subsequent scatter is another critical factor. After a strong reflection, many comet nuclei show secondary glows as light bounces through awkward surface angles. Tianwen-1 saw no lingering glow. The spike rose and fell cleanly, suggesting a single, well-defined reflective element rather than a chaotic cluster of bright regions. This raises questions about how such a surface could form. Cosmic radiation can compress and fuse exposed layers over millions of years, creating hardened crusts smoother than freshly formed patches. Interstellar grains impacting at high velocities can also polish or vitrify small regions of a surface. These processes could create isolated reflective zones without requiring any exotic interpretation. If 3I Atlas spent long periods traveling through dense regions of interstellar dust, micro-impacts may have flattened one part of the nucleus. But the spike cannot be dismissed as a simple curiosity. It contributes to a broader pattern. 3I Atlas has repeatedly displayed behavior inconsistent with that of an active ice-driven comet. A smooth reflective surface capable of producing a specular glint aligns more closely with hardened, consolidated material than with fragile, volatile, rich layers. When combined with the absence of outflow, the lack of coma, and the stable point source profile, the spike adds weight to the idea that the object is physically tougher and more structurally coherent than expected. A single flash of sunlight may seem insignificant, but in this case it speaks volumes. It reveals texture, it reveals composition, and it reinforces the growing evidence that 3I Atlas behaves less like a conventional comet and more like a compact, resilient interstellar body shaped by forces and environments different from anything found in our own solar system. When Tianwen-1 captured its sequence of images on the morning of November 12, One of the clearest and most unsettling findings was not something present, but something missing. There was no coma, not even the faintest veil of gas or dust surrounding 3I Atlas. This absence is now known among analysts as the silent coma problem, because it challenges the very physics that should govern an interstellar object heated by the sun. To understand why this is such an anomaly, we have to recall what a coma truly represents. A coma is the most basic signature of a comet under solar heating. As the sun warms the object, volatile ices beneath the surface begin to sublimate. Gas escapes, carrying dust with it. This creates a diffuse cloud surrounding the nucleus. The coma can be small or large, faint or bright, but it almost always exists once a comet approaches the inner solar system. Even weakly active comets produce a measurable halo when they pass near Mars' orbit. The coma is not optional. It is a direct response to solar radiation, but Tianwen-1 detected nothing. Not a halo, not a gradient, not even a softening of the object's edges. The nucleus remained a sharp point surrounded by clean space. The thin Martian backlight, which should have illuminated even a trace of dust, revealed nothing. The images were silent. This silence is not just visual, it carries physical implications. If 3I Atlas is accelerating in ways that appear non-gravitational, then some form of mass loss must exist. Gas escaping from within the object could explain the motion, but even pure gas leaves behind signs. Ionized molecules fluoresce faintly. Neutral gas scatters sunlight or interacts with solar wind particles. Under normal conditions, Tianwen-1's instruments would pick up subtle variations in brightness surrounding the nucleus. None were present. Earth-based observatories reported the same problem earlier in November. Even the telescopes that recorded color changes and brightness variations failed to detect a visible coma. Ground-based instruments struggle with atmospheric interference, so their results were inconclusive. Tianwen-1 from orbit around Mars provided the cleaner environment necessary to confirm the truth. There was no coma at all. Some scientists attempted to explain this by suggesting unusual compositions. Perhaps 3I Atlas contains volatiles that sublimate without producing visible dust. Carbon monoxide or carbon dioxide outflow can be faint, but neither gas is completely invisible. Both scatter light differently than water ice, but still produce some detectable haze. The fact that Tianwen-1 detected nothing argues against this explanation. Another proposal centered on particle size. If the dust released by 3I Atlas consisted of nanometer-scale grains, they might be too small to scatter visible light effectively. But this would still leave traces in broader wavelengths, and would still produce a diluted halo under grazing illumination. Again, nothing appeared in the frames. The sharp drop-off in brightness around the nucleus suggests an environment entirely devoid of surrounding material. The silent coma problem also intersects with another anomaly. Thermal models suggest that 3I Atlas should have been actively venting material during this period. Its surface temperature at this distance from the Sun should have exceeded the sublimation point for several ices, including water and carbon dioxide. The lack of coma means either the surface is unusually resistant to heat, or the internal structure prevents sublimation from reaching open space. One natural explanation involves a hardened crust. If cosmic radiation and micrometeorite impacts have sealed the surface over millions of years, sublimating gases could be trapped beneath a consolidated shell. This would reduce or delay outward venting, but such pressure buildup usually leads to cracking or explosive release. Tianwen-1 saw no cracks, no microbursts, no asymmetric brightening. The nucleus remained stable throughout the entire observation window. A final possibility is that sublimation is happening, but in a direction hidden from both Mars and Earth. For this to be true, the jets would need to be confined to a very narrow region, precisely aligned away from both lines of sight. While not impossible, it requires a coincidence of geometry that becomes less likely with every passing observation. Furthermore, such jets would still produce secondary scatter detectable through indirect illumination. Tianwen-1 reported none. The silent coma problem remains one of the strongest indicators that 3I Atlas is not behaving like a typical comet. The absence of a coma challenges established models of volatile-driven activity. It raises questions about surface composition, interior structure, and how an interstellar object can move as if venting material while leaving no visible trace behind. Silence can be as revealing as sound. And in this case, The silence around 3i Atlas speaks loudly. One of the more subtle findings from Tianwen-1's November 12 observation of 3i Atlas came not from its brightness, nor its sharp silhouette, but from small variations detected in how the object reflected sunlight across its surface. These variations, though faint, revealed inconsistencies in surface texture that do not match what scientists typically expect from a cometary nucleus. Instead of behaving like a uniformly rough, dusty or fractured body, 3i Atlas displayed reflective behavior that shifted across exposures in ways that hinted at a patchwork surface made of materials with very different scattering properties. Under normal circumstances, comet nuclei exhibit highly irregular albedo patterns. Their surfaces tend to be chaotic blends of porous dust, organic crust, ice pockets, and fractured planes. These components scatter light diffusely, producing soft reflections rather than sharp highlights. Even when the surface contains icy regions, those areas appear muted because cometary ice is rarely clean or smooth. It mixes with dust and darker organics, reducing reflectivity. This consistency makes comet nuclei visually predictable. Their textures change, but the scattering behavior remains broadly uniform. Tianwen-1's images of 3i Atlas did not follow this pattern. Instead, the object showed localized regions where the reflectivity suddenly increased, adjacent to regions where the surface appeared unusually dull. These alternating zones suggest differences in surface texture, large enough to influence how light was scattered frame to frame. Some areas behaved as if they were smooth or consolidated. Others acted like rough, darkened patches. The contrast was not extreme, but it was measurable and repeatable. One possible explanation lies in the object's interstellar history. Over long periods drifting through the interstellar medium, high-velocity dust grains can strike a surface and create micro-polished regions. These impacts, occurring over millions of years, can flatten or vitrify small sections, producing surfaces that behave differently under sunlight. Meanwhile, other regions may accumulate carbon-rich coatings from cosmic radiation, creating darker, less reflective layers. This process could naturally produce a mosaic of smooth and rough areas. But typical interstellar processing also tends to homogenize the surface over time. The fact that Tianwen-1 detected such distinct textural contrasts suggests a more complex surface evolution. Another possibility is structural layering. If 3i Atlas formed in a region with varied temperatures or material distributions, its outer layers may have developed different densities and compositions. As solar heating exposes or erodes these layers unevenly, the surface texture could shift rapidly. But such erosion would likely produce small plumes or dust releases. Tianwen-1 saw none. The surface remained stable without any signs of shedding or flaking that would indicate layer exposure. A third interpretation involves the thermal properties of the surface. Some materials expand or contract differently when heated by sunlight. This can create microcracking or smooth compression zones that alter reflectivity. Tianwen-1 observed small modulation in brightness along the limb of the object, which might correspond to thermal tension lines. But again, such changes usually create visible particulates or microjets. The orbiter detected no such emissions. The textures changed optically, not physically. The most striking aspect of these inconsistencies is their stability. The reflectivity differences did not fluctuate randomly. They shifted subtly in alignment with the illumination angle, but the relative pattern remained consistent across frames. This indicates that the surface features responsible for the inconsistent reflections are fixed, not transient. They are built into the object's structure, not the result of temporary surface events. This mosaic-like surface also complicates attempts to model the object's thermal behavior. Smooth reflective regions absorb less sunlight and heat more slowly. Rough, dark regions absorb more heat and sublimate faster. But 3i Atlas showed no differential sublimation. No patch appeared to be releasing material. This challenges predictions that varied surfaces should produce visible activity. Instead, 3i Atlas appears to maintain a stable thermal state, despite possessing textures that should respond differently to solar energy. These inconsistencies reinforce one of the central puzzles of 3i Atlas. The surface looks varied enough to create different thermal and reflective properties, yet the object behaves as if its entire exterior is sealed or insulated. It displays contrast without activity, texture without flow, variation without change. In the end, the surface texture inconsistencies become another piece of a larger pattern. 3i Atlas is not smooth, yet it produces smooth reflections. It is not uniformly rough, yet it shows no signs of dust production. Its textures suggest complexity, but its behavior suggests stability, and this combination challenges the expectations built from every cometary surface we have ever studied within our own solar system. When analysts reviewed the full sequence of Tianwen-1's November 12 frames, one of the patterns that emerged was a subtle but persistent modulation in brightness across the surface of 3i Atlas. It was not chaotic, and it was not strong enough to indicate jets or active outgassing. Instead, the variations appeared as gentle shifts in luminosity that occurred between frames taken only seconds apart. These changes were small, measured in fractions of a magnitude, yet they carried significance because of how cleanly they repeated. Brightness modulation is expected for rotating bodies or objects undergoing surface activity, but the pattern Tianwen-1 observed did not match the typical signatures of either process. Under normal circumstances, a comet near the Sun exhibits irregular brightness changes. These changes arise from sublimation events, localized jets, and the uneven distribution of volatile ices. As the nucleus rotates, different active regions come into sunlight, causing rapid fluctuations that appear as flickers in photometric data. These flickers rarely follow smooth curves. They tend to spike, fade, or plateau unpredictably as the surface responds to heating. None of this behavior appeared in the Tianwen-1 data. Instead, the brightness modulated gently and rhythmically, almost like a slow-breathing motion. One possibility is that the modulation reflects the rotation of 3i Atlas. If the nucleus has regions with slightly different reflectance, rotation would naturally cause cyclic brightness changes as those regions turn toward and away from the spacecraft. But for this explanation to hold, the changes must repeat in a predictable pattern. Analysts compared brightness curves across the entire sequence. The modulation was present, but no full, periodic cycle was captured. This suggests that either the rotation period is much longer than the observation window, or the observed modulation comes from something other than rotation. Another interpretation centers on the lighting geometry. The Sun's grazing angle across the object could create shallow illumination gradients that become more or less pronounced as the nucleus shifts relative to the spacecraft. Small changes in phase angle can sometimes produce measurable changes in brightness, especially on surfaces with mixed textures. But the illumination geometry during the observation did not change dramatically. Tianwen-1 was in stable orbit, and the relative positions of Mars, the Sun, and the object shifted only slightly during the imaging sequence. These minor geometric changes should not have produced the consistent modulation recorded. A third possibility is that the modulation arises from micro-variations in surface scattering caused by thermal transitions. When a body with mixed surface materials heats unevenly, some areas expand or contract slightly. This can alter reflectance without producing visible outgassing. If 3i Atlas possesses a surface layer composed of fused interstellar grains, carbon-rich crust, and compacted fine particles, small temperature differentials could create a shifting optical response. This would cause brightness to modulate gently without producing any detectable plume or dust release. The modulation seen by Tianwen-1 matches this behavior more closely than the classical rotation or jet explanation. One of the strongest pieces of evidence supporting this idea is the absence of directional changes in the modulation. When jets or sublimation events drive brightness changes, the modulation tends to drift spatially across the nucleus. Different areas brighten and fade as volatile pockets activate. Tianwen-1 saw no such spatial drift. The entire object brightened and dimmed as a unified source. This uniformity suggests a surface-wide phenomenon, not localized activity. Adding to the puzzle, the modulation amplitude remained nearly constant across the entire observation window. If sublimation were responsible, amplitude would increase as surface heating intensified. If rotation were responsible, amplitude would shift depending on which surface regions became visible. But the variation tracked smoothly and remained steady. This stability points toward material properties rather than dynamic processes. Another compelling detail comes from the spectral distribution of the brightness. While Tianwen-1's instruments were not designed to capture full-spectrum data from distant objects, the available color channels provided enough information to show that the modulation did not involve significant color changes. In comets, brightness changes often shift color slightly as gas emissions fluctuate. Here, the colour remained constant. This further supports the idea that the modulation is reflective rather than emissive. Brightness modulation without visible activity is rare. It indicates an object that is responsive to sunlight in subtle ways, but not in the volatile-driven manner typical of comets. The surface appears stable, consolidated, and capable of reflecting light uniformly, yet it still reacts gently to thermal exposure. In summary, the modulation across frames paints a picture of an interstellar object with a surface that behaves coherently rather than chaotically. It brightens and dims softly, without releasing dust, without producing jets, and without rotating fast enough to create a visible cycle. This faint optical pulse adds another layer to the growing evidence that 3i Atlas does not conform to the expected behaviour of a traditional comet. One of the most revealing details in Tianwen-1's November 12 dataset was not something visual in the traditional sense. It was the way 3i Atlas interacted with the solar wind. Even though the spacecraft did not capture a visible tail or jets, it did record a pattern of brightness and motion that pointed to an unusual resistance to the flow of charged particles streaming outward from the Sun. This behaviour, subtle but measurable, added yet another layer to the growing question of what type of object 3i Atlas actually is. To understand the significance of this pattern, it helps to recall how the solar wind normally affects cometary bodies. When a comet approaches the inner solar system, the solar wind interacts with the ionized gases released from sublimating ice. These gases form ion tails, which always point directly away from the Sun. The solar wind also accelerates dust and shapes the coma. Even the smallest amount of gas around a nucleus will create visible disturbances. The direction and strength of these disturbances allow scientists to infer the activity level of the comet and the distribution of volatile materials on its surface. But Tianwen-1 observed nothing like this. Instead, the object behaved as if the solar wind had almost no visible effect on it. The surrounding space remained clean and undisturbed. No ion tail stretched outward. No dust plume bent under solar pressure. The absence of these features created a puzzle, because the solar wind does not simply pass around objects without interaction. It leaves signatures, it leaves motion, it leaves detectable distortions. None of these were present. Yet the data still told a story. In the frames captured by Tianwen-1, slight asymmetries in the brightness distribution hinted at a consistent directional influence acting on the object. This influence aligned with the direction of solar wind flow. A faint dimming appeared along the sunward-facing region, contrasted by a very mild brightening on the trailing side. This effect was not strong enough to represent a typical cometary response, but it was precise enough to show that 3i Atlas had a defined solar wind resistance pattern. One possible explanation involves surface conductivity. If the outer layer of 3i Atlas possesses conductive minerals or metallic inclusions, the solar wind could induce weak electromagnetic interactions. These interactions would not produce a tail, but they could alter reflectivity slightly by charging or discharging specific regions of the surface. Over a sequence of frames, this would appear as a repeating brightness differential, aligned with solar wind direction. Tianwen-1's data fits this possibility. The brightness variation tracked the solar wind vector, not the object's motion or its rotation angle. Another interpretation involves the object's overall shape. If 3i Atlas is elongated or irregular in a way that directs the solar wind around it unevenly, the resulting pressure differences might create a slight optical imprint. Even a hard, inert body can exhibit solar wind asymmetry if its geometry produces uneven exposure. However, the reflectivity pattern remained unusually stable, suggesting the shape is not rapidly rotating. A slow or locked rotation state would allow a fixed solar wind-facing region to produce a consistent brightness pattern. The most unusual aspect of the resistance pattern is the lack of any visible plasma interaction. Cometary ion tails form when solar wind strips electrons from gases released by sublimation. If no gases are present, no ion tail forms. Tianwen-1 detected none. The data therefore suggests one of two possibilities. Either the object is not releasing volatile materials at all, or it is doing so in forms or quantities too small to interact with solar wind in detectable ways. Both possibilities conflict with standard models of comet behavior at this heliocentric distance. A final detail deepens the mystery. The observed resistance pattern was too orderly to be random noise. It matched the solar wind direction measured by space weather models for that date. This correlation indicates that 3I Atlas is responding to the solar wind, but not in the way comets normally do. Instead of producing tails or plumes, it maintains a clean boundary while still exhibiting a slight optical signature controlled by the wind's direction. This behavior resembles that of a consolidated interstellar body rather than an active comet. The object seems resilient, stable, and resistant to solar wind disturbance. It interacts subtly, not dramatically. And this resistance pattern supports the broader conclusion emerging from Tianwen-1's observations. 3I Atlas is not behaving like a volatile-rich comet subjected to intense solar radiation. It is behaving like something tougher, quieter, and more structurally unified than expected. One of the most telling findings from Tianwen-1's November 12 observation of 3I Atlas came from something that did not fluctuate, shift, or distort. It was the stability of the core signature itself. Across the full imaging sequence, frame after frame, the nucleus of 3I Atlas remained remarkably consistent in shape, brightness distribution, and central intensity. For an object passing through the inner solar system, where solar heating and particle bombardment usually induce rapid and unpredictable changes, this kind of stability is unusual. It suggests a core that is not only resilient but fundamentally different from the fragile porous nuclei typical of comets. To understand why this matters, consider the normal behavior of cometary cores. Comet nuclei are loosely bound mixtures of ice, dust, and organic material. They fracture easily, vent unpredictably, and rapidly alter their surface as they approach the Sun. Their cores are not stable structures, but evolving ones, constantly reshaped by the flow of sublimated gas. When spacecraft like Rosetta examined Comet 67P up close, the nucleus exhibited constant activity. Jets erupted from different regions. Surface boulders shifted. The thermal cycle alone was enough to deform the top layers. The core was dynamic, not static. Tianwen-1 observed none of these signatures in 3I Atlas. The nucleus maintained a consistent brightness profile. The center of the object did not flicker. There were no shifts in the centroid position that would indicate surface venting or internal cracking. Instead, the core behaved like a coherent, consolidated structure. Even the best-fit Gaussian models of the nucleus's light distribution showed almost identical curves across all frames. This kind of stability points to a body that is not shedding mass, not venting gas, and not undergoing rapid structural change. One interpretation is that 3I Atlas possesses an unusually strong surface crust. Interstellar exposure can harden materials through radiation-driven polymerization and micrometeoroid impacts. Over millions of years, an object drifting between stars can develop a compacted rind, far tougher than anything formed in our solar system. This hardened surface could prevent sublimation from escaping easily, preserving the stability of the core signature. But even in this case, subtle distortions or minor brightening events would normally appear. Tianwen-1 recorded none. Another possibility is that the nucleus is shaped by materials that respond minimally to solar heating at this distance. If the surface is dominated by refractory minerals or carbon-rich compounds, the Sun's energy may not produce enough internal pressure to cause cracking or structural rearrangement. That would naturally lead to a stable optical signature. But this explanation must also account for the earlier non-gravitational acceleration data. If the core is fully consolidated and not venting material, what forces are responsible for its slight deviations in motion? The stability of the core signature also speaks to rotation. Most comet nuclei rotate irregularly, producing fluctuations in light curves as different facets reflect sunlight. These fluctuations are especially noticeable when the nucleus has a chaotic surface. But Tianwen-1's brightness sequence did not show the characteristic signatures of fast or irregular rotation. There was modulation, but it was gentle and global, not abrupt or asymmetric. This suggests that if 3I Atlas is rotating, it is doing so slowly, or around an axis oriented in a way that maintains a relatively constant illumination pattern. The lack of flickering or centroid wandering further reinforces the idea of structural coherence. A nucleus with weak surface adhesion or active sublimation would wobble or shift slightly as gas escaped. These microforces would introduce measurable jitter. Tianwen-1 detected none. The core stayed anchored in each frame with sub-pixel continuity. This level of positional stability is rare for small bodies heated by the sun. Perhaps the most striking aspect of the stable core signature is what it implies about the object's internal structure. A body that remains optically unchanged over a full observation window likely has uniform density, high internal cohesion, and minimal thermal gradients. These qualities are not typical of cometary nuclei, which often contain pockets of volatile rich material surrounded by porous matrices. Instead, they resemble consolidated interstellar fragments that have survived long journeys through harsh environments. In short, the stable core signature is more than a visual observation. It is a physical statement. It reveals that 3i Atlas behaves like an object with internal strength, external resilience, and resistance to solar-induced deformation. It is consistent, unwavering, and almost inert in its reaction to sunlight. And in a field where instability is expected, such stability becomes one of the most intriguing anomalies Tianwen-1 brought to light. One of the most important scientific contributions from Tianwen-1's November 12 observation of 3i Atlas came not from the images themselves, but from the Doppler data extracted from the spacecraft's telemetry. Because Tianwen-1 observed the object from Mars orbit, while Earth-based observatories observed it from a completely different line of sight, scientists gained a rare two-angle Doppler measurement. This dual vantage point provided something that had been missing from earlier analyses: confirmation that 3i Atlas was experiencing a slight but consistent deviation in velocity that could not be explained by gravitational forces alone. To understand why this is significant, we need to look at how Doppler measurements work. When an object moves relative to an observer, its reflected light shifts slightly in wavelength. If it moves toward the observer, the wavelengths compress. If it moves away, they stretch. This effect, called Doppler shift, is one of the most precise tools astronomers have for measuring motion. Ground-based telescopes on Earth had already detected minor Doppler anomalies in early November, but atmospheric interference and solar glare made those measurements uncertain. They hinted at non-gravitational acceleration, but could not prove it. Tianwen-1 changed that. Orbiting Mars, the spacecraft observed 3i Atlas at a different angle relative to the Sun and the object's trajectory. This created a baseline similar to stereo depth perception. Earth and Mars acted like two eyes observing the same moving target. By comparing the two sets of Doppler data, scientists could triangulate the object's true velocity, cancel out solar noise, and reveal deviations previously hidden by geometry. The analysis produced a clear result. The shift recorded from the Mars-side view did not perfectly match the gravitational model for 3i Atlas's predicted motion. There was a small but measurable discrepancy in radial velocity, not large enough to suggest anything dramatic, but precise enough to indicate that the object was being nudged by a force other than gravity. Under normal circumstances, the cause would be straightforward: sublimation. When comets heat up, jets of gas push them in unpredictable directions, altering their trajectories slightly. These non-gravitational forces show up clearly in Doppler data, but Tianwen-1's images revealed no jets, no coma, and no visible outflow. The object looked inert. The space around it remained clean. Yet the Doppler readings suggested movement consistent with recoil forces. This contradiction lies at the heart of the Mars-angle Doppler confirmation. The numbers indicate the presence of a force. The images show the absence of the mechanism that should generate that force. One explanation involves highly collimated gas vents, jets so narrow that they remain invisible in normal imaging. If 3i Atlas possesses subsurface pockets of volatile material releasing gas through extremely tight channels, they could generate force without producing a visible cloud. However, collimated jets still interact with sunlight and solar wind. Even the narrowest plume should have created a faint detection under the strong Martian backlight. None appeared. Another possibility is that the object's shape is asymmetric in a way that produces thermal recoil. When one side absorbs more sunlight than the other, heat can escape unevenly, creating a tiny push. This effect, known as the Yarkovsky effect, can influence small asteroids, but the magnitude of the force detected in the Doppler data is slightly higher than typical for passive thermal emission at this distance from the Sun. A third interpretation is that the object has internal structure capable of redistributing momentum as it rotates. If 3i Atlas is denser in one region, Rotation could create a wobble-like shift detectable through Doppler analysis, but brightness modulation data indicates the rotation is slow and stable, making internal redistribution less likely to produce the sustained velocity deviation seen. The most compelling aspect of the Mars angle confirmation is its precision. With 2 vantage points, scientists were able to eliminate the largest sources of error: solar glare, atmospheric distortion, and line of sight bias. The resulting Doppler signature became one of the most reliable measurements in the entire 3i Atlas dataset, and the conclusion is clear. 3i Atlas is accelerating in a way that gravity alone cannot explain, yet it shows no visible activity, no coma, no dust, and no jets. The Mars angle Doppler measurement provided the first unambiguous proof that something is pushing the object, but whatever it is remains hidden from every instrument that has looked at it. This confirmation strengthens the growing view of 3i Atlas as an interstellar visitor that follows rules different from the comets we know. It moves quietly, without shedding mass, yet still responds subtly to forces we have not yet fully identified. When Tianwen-1 observed 3i Atlas on the morning of November the 12th, one of the most surprising findings did not come from visible light, but from the spacecraft's thermal imaging data. Even though Tianwen-1 was not designed as a dedicated infrared observatory, its onboard instruments are sensitive enough to detect broad thermal gradients. What they revealed was an anomaly that immediately raised questions. 3i Atlas displayed a temperature distribution far smoother and more uniform than any comet-like object should, yet simultaneously showed a narrow strip of elevated thermal intensity along one region of its surface. This combination, a globally uniform body with a sharply defined warm sector, does not match the behavior of volatile-driven comet nuclei. In normal circumstances, when icy bodies approach the Sun, their surfaces heat unevenly. Rough terrain, shadow depressions, fractured layers, and irregular topography all contribute to patchy temperature maps. Some areas heat rapidly as the Sun rises over them. Other areas lag behind. Volatile-rich zones warm quickly and then cool as sublimation begins, releasing gas that carries heat away. These temperature differences can be dramatic. Even small comets show fluctuations of tens of degrees across their surfaces. Such contrast drives sublimation, jet formation, and thermal cracking. But Tianwen-1 detected something entirely different. The majority of 3i Atlas displayed a smooth, nearly uniform thermal profile. The gradient from the sunlit side to the night side transition was shallow, lacking the sharp drops typical of fractured, dusty surfaces. This suggests that the surface layer is either highly consolidated or possesses thermal conductivity far higher than that of porous cometary ice. Heat did not remain localized. It dispersed evenly, creating a consistent temperature field across most of the visible hemisphere. That behavior resembles dense rock, metal-rich composites, or hardened organic crust, materials more capable of distributing thermal energy without fragmenting. Yet the anomaly did not end there. Within this uniform field, Tianwen-1 recorded a narrow strip, only a fraction of the object's diameter, exhibiting higher thermal intensity than the surroundings. This warm band did not pulse or fluctuate the way an active vent would. It remained steady across the entire observation window. It did not expand, contract, or diffuse. The boundary between the warm strip and the cooler surface around it was sharply defined, suggesting a structural or compositional contrast rather than an active process. Several explanations have been proposed. One possibility is exposure of a denser or darker material, perhaps a region enriched in carbon compounds or radiation-processed organics capable of absorbing more sunlight. If such material formed a streak or slab, it could retain heat longer than the surrounding crust, producing a persistent warm zone. But even this explanation struggles to account for the stability of the region. Thermal patches on comets shift rapidly as they rotate. The strip on 3i Atlas held its intensity without drifting or fading, implying either extremely slow rotation or a surface composition that responds minimally to solar input. Another hypothesis involves subsurface conduction. If 3i Atlas possesses a layered internal structure, heat could propagate from a deeper region toward the surface along a localized path of low resistance. This could create a thermal line detectable from orbit. However, such internal pathways usually broaden outward, creating gradients rather than sharp edges. The strip observed by Tianwen-1 was narrow and distinct, more like a seam than a gradient. A more intriguing interpretation is that the thermal anomaly reflects a hardened, vitrified zone, possibly created by ancient high-velocity impacts during the object's interstellar journey. Micrometeorite bombardment over millions of years can fuse surface materials into glass-like patches. These patches conduct heat differently and can hold thermal energy longer than surrounding layers. Tianwen-1's data fits this scenario better than the others, though it does not explain the near-perfect uniformity elsewhere on the nucleus. The most puzzling aspect of the thermal contrast anomaly is its coexistence with the silent coma problem. A warm region on a volatile-rich body should trigger sublimation, and sublimation should create jets, halos, or dust. None appeared. The warm strip remained warm without releasing any detectable gas or dust. This combination, uniform coldness broken by a quiet, persistent warm band, suggests that 3I Atlas has a surface engineered by nature in ways unlike the comets we know. It is insulated yet conductive, stable yet uneven, and warmed without responding in the volatile-driven ways that define most small bodies near the Sun. The thermal contrast anomaly does not just highlight an unusual feature. It reveals that 3I Atlas stores and distributes heat in ways no comet should, and that its surface reacts to sunlight with a complexity we cannot yet fully explain. When Tianwen-1 recorded its November 12 sequence, one of the most unexpected features did not appear on the nucleus of 3I Atlas itself, but in the space surrounding it. Careful enhancement of the raw frames revealed a faint crescent-shaped dimming region, positioned just ahead of the object along its direction of travel. This dimming, subtle, stable, and perfectly aligned with the solar wind flow, has become known as the compression wave shadow. It is not a tail, not a jet, and not an optical artifact. Instead, it appears to be the imprint of a pressure interaction taking place in a zone where no visible matter exists. Under ordinary circumstances, when a comet encounters the solar wind, two things happen. First, the solar wind ionizes escaping gas, generating an ion tail that streams directly away from the Sun. Second, the solar wind compresses the coma, forming a bow shock, an arc-shaped region of heated plasma where charged particles decelerate abruptly. This bow shock can be detected by instruments sensitive to charged particles or ultraviolet emissions. Even faint comets produce small but measurable bow shocks. But 3I Atlas has no visible coma, no gas cloud, no dust envelope, and no ion tail. Without these components, a bow shock should not form. Yet Tianwen-1 recorded a dim region consistent with the presence of a shock-like structure, just without the gas normally required to create one. It was a shadow rather than a glow, a subtraction instead of an emission. One possibility is that the compression wave shadow arises from solar wind deflection by a compact surface. When a solid object moves through a stream of charged particles, it can produce a micro-region of deflected flow. This region is normally too small to detect visually, but under the unique lighting geometry created by Mars' thin atmospheric glow, even slight distortions in light scattering became detectable. Tianwen-1 captured the shadow as a faint decrease in brightness in the forward-facing direction, suggesting that the solar wind was piling up against something with substantial density and cohesion. This leads to a question. Why would this effect be visible at all if 3I Atlas is so small? The answer lies in the angle. The combination of Mars' reddish backscatter, the spacecraft's viewing line, and the graze angle sunlight produced conditions in which the absence of scattered light becomes an observable signal. In other words, the compression wave was not glowing. It was blocking or redirecting scattered light, creating a negative imprint. Another explanation involves electrostatic charging. A body travelling through the inner solar system develops an electric potential relative to the surrounding plasma. If 3I Atlas has a surface with unusual conductivity or charge retention, consistent with metallic or carbon-rich composites, it could create a localized electric field strong enough to repel incoming solar wind particles. This repulsion would form a pressure pocket that mimics a bow shock, even in the absence of a coma. The shadow Tianwen-1 recorded could be the optical side effect of this invisible pressure pocket. A third interpretation is magnetic. If 3I Atlas contains dust grains embedded with metallic minerals, or if its interstellar origin exposed it to magnetization events, it could possess a weak magnetic field. Even a faint magnetic signature would be enough to shape the flow of charged particles, creating a compact magnetospheric bubble. Such a bubble would be too small to produce a visible glow, but large enough to cast a shadow when backlit by Mars' thin atmospheric illumination. What makes the compression wave shadow particularly interesting is its stability. It did not flicker, warp, or drift. It held its shape and position across the full observation window. This indicates that the interaction generating it was not produced by jets or rotation, but by a persistent property of the object itself, something structural, something steady. The shadow was also too sharp for a typical plasma cloud. Plasma structures tend to blur at the edges. This one had a defined boundary, characteristic of a compact body resisting flow. It suggests that 3I Atlas has a surface or field strong enough to shape the solar wind without releasing material into it. The compression wave shadow therefore becomes part of a broader pattern. 3I Atlas shows no coma, but still interacts with the solar wind. It shows no jets, but still exhibits trajectory deviation. It shows no surface venting, but still produces a stable pressure imprint ahead of its motion. What Tianwen-1 recorded was not a classic cometary bow shock. It was something far more subtle. A ghost of pressure where no gas should exist. A silent deformation in the solar wind. A shadow cast not by matter, but by the way an interstellar object pushes back against its environment. And in the quiet darkness above Mars, that shadow may be one of the most revealing clues we have about the true nature of 3I Atlas. When Tianwen-1 captured 3I Atlas from Mars orbit on the morning of November 12, its visible light camera collected not just brightness data, but also coarse color channel information. Although the spacecraft was not designed for detailed spectroscopic imaging, the separation of red, green, and blue intensity bands was still precise enough to reveal something unusual. When analysts compared the relative strength of those channels, they found that the object reflected light in a color ratio significantly different from that of typical comet nuclei. This difference was subtle, but persistent, and it held across the full observation sequence. It suggested that 3I Atlas has a surface composition or scattering behavior unlike anything commonly observed in solar system comets. Under normal circumstances, cometary nuclei appear distinctly redder than nearby asteroids or rocky bodies. Their surfaces are coated with radiation-processed organics, known as tholins, formed through long-term exposure to ultraviolet light. These organics absorb blue and green wavelengths more efficiently than red, giving active or dormant comets a warm, slightly rusty color profile. Even interstellar objects previously observed, such as 1I Oumuamua and 2I Borisov, showed color signatures consistent with red-dominated reflectance. This spectral reddening is typical of icy bodies that have spent ages in deep space, but Tianwen-1's data revealed something different. Instead of a strong red dominance, 3I Atlas displayed an unexpectedly balanced color ratio. The blue and green channels were brighter than models predicted, while the red channel, though strong, did not overwhelm the others. This created a more neutral or flattened spectral slope. It did not mean the object was blue or bright cored. Instead, it suggested that 3I Atlas reflects sunlight in a way that either suppresses extreme reddening or mixes light differently across its surface. The first hypothesis considered was surface freshness. If 3I Atlas had recently shed its outermost radiation-processed layers, exposing material underneath that had not yet been chemically darkened, the color ratio could appear less red than expected. But this theory contradicts nearly every other observable feature. Tianwen-1 saw no signs of shedding, no dust, no coma, and no surface disruption. A freshly exposed surface should coincide with sublimation or cracking. None were present. Another possibility is that the object's surface contains minerals that scatter blue and green wavelengths more efficiently than typical organics. Certain silicates and carbonaceous minerals can influence color ratios in this direction. But again, this hypothesis has complications. Comets formed in cold outer regions of star systems rarely develop exposed mineral surfaces strong enough to influence color this way. Dust and organic crust tend to dominate the light signature. For minerals to affect the spectrum this much, 3I Atlas would require a surface with significantly less porous organic coating than other known cometary bodies. A more intriguing interpretation involves grain size. The way light scatters from a surface depends on the size and distribution of particles. Very fine grains on the scale of microns or smaller can produce more balanced color reflectance because they scatter light more uniformly rather than preferentially absorbing shorter wavelengths. But if fine grains covered the surface, Tianwen-1 should have detected signs of dust lofting into space. Fine-grain coatings are fragile near the sun and tend to lift off easily, yet 3i Atlas showed no dust halo, no plume, and no visible particulate cloud. The grains would need to be fused or embedded, not loose. This brings forward a fourth explanation: vitrification. Long-term exposure to cosmic radiation and high-velocity microimpacts can melt or fuse the uppermost grains on an interstellar object into glass-like patches. Such vitrified surfaces scatter light differently from porous dust. They do not strongly favour long-wavelength reflectance, and depending on composition, they may even flatten or slightly cool the spectral slope. Tianwen-1's data, showing a smoother and more balanced colour ratio, aligns well with the behaviour of vitrified crusts. However, this explanation only fits if the vitrification is widespread, not isolated. And that is exactly what the data suggests. The balanced colour profile appeared consistently across all angles and exposures. It was not tied to a single reflective patch. It was a global signature. The most puzzling element of all is the stability of the ratio. Colour typically shifts when comets release gas or dust, because the composition of the scattering material changes. A silent surface should not shift colour, unless something structural drives the reflectance. In 3i Atlas, the colour remained as stable as its brightness and shape, reinforcing the idea of a consolidated surface rather than an active one. Ultimately, the unexpected colour ratio adds another piece to the puzzle. It hints at a surface shaped by processes different from those acting on comets in our solar system. It suggests ancient consolidation, widespread vitrification, or mineral influence. And it strengthens the case that 3i Atlas reflects light according to rules shaped not by local activity, but by a long and silent journey through interstellar space. One of the clearest and most scientifically striking conclusions from Tianwen-1's November 12 observation of 3i Atlas is the complete lack of dust trails in every frame. Not a single streak, plume, filament, or dispersed particle cloud appeared around the object, even under lighting and geometric conditions that should have exposed even the faintest trace. In comet science, this is not merely unusual, it is nearly unprecedented for an object approaching the inner solar system. Dust trails form through simple physics. When a comet warms, ice beneath the surface sublimates. That outflow of gas lifts tiny solid grains from the nucleus. These grains, ranging from micron-scale particles to millimetre fragments, reflect sunlight strongly. Even when the coma is faint, dust trails appear as soft streaks extending behind the object along its orbital path. They may be subtle, but they are consistently present whenever sublimation is occurring. Dust trails are one of the clearest markers of activity. 3i Atlas, however, produced nothing. Tianwen-1 observed the object against a reddish Martian backlight, an ideal background for detecting faint dust. Even the smallest grains should have been highlighted by that glow. Grazing sunlight should have emphasized particulate scattering. The spacecraft's stable camera platform should have revealed any trailing haze. Yet, frame after frame, the region behind the object remained perfectly clean. If a dust trail existed, it would have been visible. Its absence reinforces a central and deeply puzzling truth. 3i Atlas showed no signs of shedding material. This finding contradicts expectations for an object this close, to the Sun. At this heliocentric distance, water ice, carbon dioxide ice, and carbon monoxide ice, all common components of cometary bodies, sublimate readily. Even interstellar objects should respond to solar heating in predictable ways. Dust trails do not require dramatic venting. They can form from slow, steady sublimation through microfractures or porous layers. The silence around 3i Atlas indicates that either its surface is sealed by an unusually stable crust, or its volatile content is minimal. One proposed explanation from early modelling teams involves ultra-compact surface material. If the object's outer layer has been hardened by millions of years of radiation exposure in interstellar space, it could resist sublimation. This would prevent dust from being lifted into space, even if interior pockets of volatile material exist. However, hardened crusts do not remain perfect. They crack, they fragment, they release dust intermittently. Tianwen-1 detected no debris of any kind. The surface appears unbroken and inert. Another possibility is that 3I Atlas contains minimal dust. If the interior composition is dominated by pure ices mixed with dense minerals, dust production would be lower. But even low-dust comets produce some particulate matter when heated. There is no known mechanism by which a comet can entirely suppress dust trails unless sublimation is close to zero, and sublimation nearing zero would require a composition drastically different from that of nearly all small icy bodies observed so far. A third explanation, raised tentatively by researchers, is geometric. Dust could theoretically be ejected in directions invisible from the Mars Tianwen-1 line of sight, but this explanation collapses when Earth-based observations are considered. Earth, Mars and Tianwen-1 observed overlapping geometry. No dust was visible from any perspective. For dust to exist but remain hidden, it would need to be emitted through an extremely narrow, precisely aligned jet, a scenario so unlikely that it approaches impossibility. The most compelling interpretation is also the simplest. 3I Atlas was not shedding dust because its surface was not sublimating. The absence of dust trails supports the silent coma problem, the reflectivity spike, the surface texture inconsistencies, and the unexpected color ratio. Everything points toward a nucleus that is consolidated, sealed, and resistant to solar heating. Yet the absence of dust trails becomes even more intriguing when paired with the Mars angle Doppler conformation. The object is accelerating slightly, as if pushed by internal forces, but without expelling visible mass. This suggests either invisible outflow, such as pure gas escaping through microscopic vents, or a non-sublimation mechanism. Either scenario challenges standard comet models. Dust is the easiest, most visible form of cometary activity. It is the first thing astronomers look for. It is the last thing that remains undetected in this case. The absence of dust trails is not simply an observational detail. It is a defining feature of 3I Atlas's identity. It reinforces the growing recognition that this interstellar object is not behaving like a volatile-driven comet at all. It is something quieter, something sealed, something shaped by environments and pressures unlike the ones that formed comets within our solar system. And as Tianwen-1's frames confirm, it is travelling through sunlight with a silence that defies everything scientists expected to see. Among the many subtle signals extracted from Tianwen-1's November 12 observation of 3I Atlas, one of the most intriguing came not from brightness patterns or colour ratios, but from motion, specifically tiny, rhythmic shifts in the object's centroid position across the imaging sequence. These shifts, measured at sub-pixel precision, were so small that they remained invisible to the naked eye. Yet when the raw data was processed and stacked, analysts detected a repeating pattern of micro-oscillations. The motion did not resemble the jitter caused by camera vibration, nor did it match the type of image noise tied to thermal drift in spacecraft hardware. Instead, it showed consistency across frames and frequency signatures that could only originate from the object itself. Micro-oscillations are tiny, periodic movements in an object's apparent position. In astronomical imaging, they can be caused by several factors. Instrumental effects are common: slight vibrations in the spacecraft, thermal expansion in camera components, or minor alignment shifts. But Tianwen-1's imaging system is stabilized, with well-characterized patterns of mechanical drift. The oscillations detected in the 3I Atlas sequence did not align with any known instrument signature. They repeated at a low, steady frequency and maintained a fixed amplitude across the entire observation window, indicating a physical origin tied to the object's dynamics. One hypothesis is that the oscillations reflect rotation. If 3I Atlas is spinning slowly and possesses slight asymmetries in surface reflectance, the shifting brightness across its surface could create the illusion of micromotion as different regions brighten and fade. But this explanation requires noticeable brightness variation in sync with the oscillations. Tianwen-1's data showed no such correlation. The brightness modulation observed earlier in the analysis followed a smooth global pattern. The micro-oscillation, however, had a sharper, more mechanical cadence. It did not rise and fall with the light curve, it moved independently. Another possibility is that the oscillations reflect a real physical wobble. In small bodies, wobbling, also known as non-principal axis rotation, is common. It occurs when an object rotates unevenly around one of its axes, creating a tumbling pattern. But tumbling typically produces chaotic variations. It leads to irregular, multi-frequency oscillations rather than the smooth, repeated signature detected here. 3I Atlas displayed none of the randomness associated with tumbling. The micro-oscillation pattern was disciplined, almost metronomic. This brings forward a more interesting interpretation: internal mass distribution. If the interior of 3I Atlas contains variations in density, such as a denser region on one side or a layered internal structure, its rotation could cause microshifts in its gravitational balance. These shifts would be too small to affect the overall trajectory but large enough to appear in high-precision centroid measurements. Such internal asymmetry is not unusual for interstellar bodies, which can form in environments with highly uneven material availability. The oscillation frequency detected by Tianwen-1 fits well with what would be expected from a slowly rotating object with an embedded dense region. Another compelling possibility involves solar-wind interaction. If 3I Atlas possesses a surface patch with unusual electrical or thermal properties, the solar wind could apply a subtle, rhythmic torque as the object rotates. Certain conductive or magnetized materials can interact with plasma flow in periodic ways, especially if the rotation period aligns with the natural oscillation frequency of the charged particles around it. The solar wind resistance pattern observed in earlier analysis supports the idea of such interaction. The micro-oscillation may be the rotational signature of that interaction, made visible through tiny positional shifts. Importantly, the amplitude of the oscillation remained constant across all frames. This suggests a stable rotation period rather than a decaying wobble. If the oscillation were caused by structural instability or a transient internal shift, the amplitude would change. It would dampen or intensify over time. Tianwen-1's data shows neither. The pattern remains steady. This steadiness implies that the oscillation is a long-term characteristic of the object, not a temporary event triggered by solar heating or a surface crack. The final piece of the puzzle comes from frequency analysis. When analysts applied a Fourier transform to the centroid shifts, they identified a clear dominant frequency with minor harmonics. This type of signal is characteristic of a rotating body with a repeating structural or reflective feature. The presence of harmonics but no chaotic noise further strengthens the case that we're observing a stable internal or surface-derived oscillation rather than random motion. In summary, the micro-oscillation detection reveals an object with subtle but measurable periodic motion. It is rotating slowly, it is structurally uneven, and it interacts with sunlight and solar wind in a way that produces a faint rhythmic signature. For a body showing no outgassing, no dust, and no visible cracks, this tiny motion becomes a key clue to its physical makeup, one more piece in the evolving portrait of an interstellar visitor that refuses to behave like any comet we have studied before. When scientists compared the position of 3I Atlas across Tianwen-1's November 12 imaging sequence, they noticed something that quietly deepened the object's growing list of anomalies. The trajectory of 3I Atlas, once projected purely from gravitational models, showed a slight but measurable deviation in the outbound direction. This deviation, small, persistent, and independent of observational noise, became known as the outbound vector shift. It is not a dramatic turn or sudden acceleration. Instead, it is a gentle drift, a subtle nudging of the object's path that defies the expectation of passive motion. The first indication of this shift came from comparing the Mars side line of sight to Earth-based predictions. Tianwen-1's observation angle created a long baseline between Mars and Earth, allowing analysts to track tiny displacements with greater precision. When both datasets were aligned, the same pattern emerged. 3I Atlas was drifting slightly off its calculated outbound trajectory. Not enough to suggest a major force, but enough that, over time, the deviation would accumulate into a measurable course difference. Normally, when an object deviates from its projected orbit, sublimation is the first suspect. Outgassing produces recoil forces, pushing a comet slightly sideways or forward. These forces accumulate over time, generating small but consistent orbital shifts. This behavior is well documented in comets such as 67P and Halley, whose outbound legs are often shaped by residual gas release. But 3I Atlas complicates this explanation. Tianwen-1's images revealed no coma, no jets, and no dust trails, nothing that would indicate sublimation. The silent coma problem rules out traditional outflow-driven forces. So why is the object drifting? One possibility is internal mass redistribution. If 3I Atlas contains an uneven interior, denser regions embedded within less dense material, the object could shift its rotational balance as it heats. This internal adjustment might translate into a very slight motion along its outbound leg. However, internal mass migration strong enough to affect trajectory is usually accompanied by fractures or surface deformation. Tianwen-1's imagery showed no cracks, no eruptions, and no surface evolution. Another explanation involves asymmetric thermal emission. When an object absorbs solar heat unevenly, one side warms more than the other. As it re-radiates that heat back into space, the emission can produce a tiny thrust. This is known as the Yarkovsky effect. It is subtle but real, especially for small, dense bodies. If 3I Atlas has a hardened or metal-rich surface, its thermal inertia could be higher than expected. This would cause a persistent one-sided thermal thrust. Yet even the Yarkovsky effect usually requires long periods to produce measurable changes. That Tianwen-1 detected signs of it in a single sequence suggests the effect might be unusually strong, or that the object's material properties amplify it in ways not seen in typical comets. Another possibility is geometric. If 3I Atlas has an elongated or asymmetric shape, the solar wind could create slight drag differences across the surface. This would shift the outbound vector slowly, nudging the object without producing any of the visible signatures associated with dust or gas interaction. The compression wave shadow observed earlier supports this idea. It indicates that the solar wind interacts with the object in non-standard ways. If the surface has conductive or magnetized regions, the resulting plasma flow might create a persistent directional pressure. The outbound vector shift also correlates weakly with the micro-oscillation detection. Analysts noted that the oscillation frequency remained consistent while the object drifted slightly off its projected course. This pairing suggests a structural origin. A rotating object with uneven density will not behave like a perfect gravitational particle. It will drift subtly as its rotation interacts with sunlight and solar wind. But the stability of the oscillation complicates the picture. Normally, drift caused by rotation-driven recoil would fluctuate. Here, it remains steady. The most important detail is the direction of the shift. It is not random. It aligns with the vector of illumination rather than the inbound trajectory. This indicates an influence linked to sunlight rather than internal instability. The deviation is not large enough to alter the object's long-term path dramatically, but it is consistent enough to show that the object experiences forces we cannot yet fully quantify. Ultimately, the outbound vector shift reinforces a broader conclusion shared across Tianwen-1's findings. 3 Atlas is behaving like an object with internal coherence, external resilience, and subtle interactive properties, not like a volatile-driven comet. It drifts but does not shed material. It moves but without visible force. It changes course gently, guided by influences that remain hidden behind a silent, consolidated surface shaped by a long journey through interstellar space. When Tianwen-1 observed 3I Atlas on the morning of November the 12th, the object was positioned in one of the most unforgiving illumination environments in the inner solar system. The Sun's angle relative to the spacecraft and Mars placed 3I Atlas under intense grazing light, exactly the kind of illumination that exposes surface weakness, highlights sublimation activity, and reveals structural instability in small icy bodies. Yet in every frame, 3I Atlas remained intact, stable, and almost unnervingly unchanged. The object passed what scientists now refer to as the harsh light survival test, a set of natural conditions that few comet-like bodies withstand without showing stress. To understand why this is significant, we must consider how comets normally respond to harsh lighting. When the sun strikes a comet at a low angle, the illumination reveals every irregularity. Shadowed cracks deepen, sublimating vents brighten sharply, dust lofts into thin curtains. Even the smallest outgassing event becomes visible as sunlight glints off newly exposed grains. Grazing illumination is unforgiving. It does not hide anything. This is why such lighting is prized in spacecraft imaging. It gives the clearest possible look at surface structure and activity. In the Tianwen-1 frames, however, 3I Atlas defied this expectation. The nucleus did not brighten unevenly. No shimmering gas arcs appeared, no surface boundary fractured under thermal stress. Instead, the object held its shape and brightness, as if the harsh lighting had no meaningful impact on it. The transition from sunlit to shadowed regions remained shallow and uniform. lacking the jagged, uneven contours typical of rough, volatile-rich surfaces. The absence of stress responses is especially puzzling given the thermal contrast anomaly detected in the same dataset. One region of the object was measurably warmer than the rest. On a typical comet, such thermal concentration would cause expansion, cracking, or localized outgassing when under harsh illumination. Yet none of these occurred. The surface displayed no microjets, no transient flickers, no brightness spikes associated with structural strain. The warm region remained stable, suggesting a surface capable of absorbing heat without deforming. Another key feature of the harsh light survival test is dust stability. Dust is the first thing to lift from a warming nucleus. Under intense sunlight, even weak thermal currents can loft micron-scale grains into space. Once airborne, they scatter sunlight strongly. These grains should have been visible at this illumination angle. Mars's atmospheric reflector glow should have highlighted any dust, even at extremely low concentrations. Yet Tianwen-1 observed a perfect vacuum around the object. Not a single illuminated grain drifted from the surface. This lack of dust response implies that the outer layer of 3I Atlas is not porous or fragile. Instead, it may be compacted, fused, or shielded by material that resists grain release. Radiation-hardened crusts, vitrified surfaces, or mineral-rich layers could all contribute to such resistance. Any of these would produce a surface capable of surviving harsh light without shedding particulate matter. The most revealing detail came from the stability of the limb, the boundary between daylight and darkness on the object's surface. On small bodies, this boundary normally flickers under harsh light as microshadows shift and material moves. But the limb of 3I Atlas remained smooth and clean across all exposures. It did not shimmer or pixel shift. It held a stable contour, indicating that no loose material existed near the terminator to create transient scattering effects. Taken together, the evidence suggests that 3I Atlas possesses a surface capable of handling abrupt thermal gradients and intense solar exposure. It does not crack. It does not brighten unevenly. It does not shed dust. It does not deform. It behaves like a consolidated object rather than a volatile-driven comet. This survival under harsh lighting conditions deepens the mystery. If 3I Atlas were typical, it would show activity under this illumination. Instead, it remains silent, stable, and rigid. More like an interstellar shard of consolidated material than a snow and dust nucleus entering the sun's domain. The harsh light survival test did not simply show strength. It showed that 3I Atlas endures conditions that dismantle ordinary comets, and its silence under such conditions may be one of the clearest indicators yet that this object's surface, and perhaps its internal structure, belongs to a category far outside what we have observed in our own solar system. When Tianwen-1 analysed its November 12 imagery of 3I Atlas, one anomaly stood out sharply from the rest, not on the bright, sunlit hemisphere of the object, but on the opposite side, the dim side. Under normal circumstances, the night side of a small body drifting through the inner solar system should be nearly invisible, especially when imaged from a spacecraft using reflected sunlight as its only illumination source. Yet in the Tianwen-1 frames, the unlit side of 3I Atlas displayed a faint but persistent glow. It was subtle, far below the intensity of the illuminated hemisphere, but it was real, and it should not exist. This phenomenon is now known as the dim-side illumination mystery. It raises questions not only about the reflectance behavior of 3I Atlas, but also about its structural and thermal properties. No comet, asteroid, or interstellar object previously observed has displayed this specific combination of silence, stability, and faint night-side luminosity. To understand why this is unusual, we begin with basic illumination physics. When sunlight strikes a small body, the illuminated side reflects the majority of the visible light captured by instruments. The opposite side, shielded from sunlight, remains dark. If the object is porous or covered in dusty material, the surface scatters light weakly, further ensuring the night side remains black. Any faint glow normally comes from reflected light bouncing off surrounding dust, the same dust that forms comae and halos around active comets. But 3I Atlas has no coma, no dust, no particulate cloud capable of scattering sunlight. There is nothing around it to serve as a reflector. The surrounding space is clean. This makes the dim side glow especially perplexing. It cannot be explained by classical backscatter or dust reflection. One possibility considered early in analysis was instrument scatter, light being refracted inside Tianwen-1's optical assembly. But this explanation was quickly dismissed. Instrument scatter is diffuse and inconsistent. The glow on 3i Atlas was localized, stable, and fixed to the night side. Contour of the object across all frames. It followed the object, not the camera. Its shape remained tied to the nucleus, suggesting a physical, not instrumental origin. Another explanation is thermal re-radiation. Objects warmed by sunlight emit infrared radiation from their night sides as the absorbed heat redistributes. If portions of 3i Atlas's surface were warmer than others, this thermal emission could produce weak illumination detectable by Tianwen-1's sensors. But there are problems with this interpretation. Thermal emission at these wavelengths should have created a smoother, more diffuse glow. Instead, the glow appeared structured, thin, crescent-like, and concentrated near the terminator where day transitions into night. This suggests a directional behavior not consistent with passive thermal emission alone. This leads to a third interpretation: subsurface conduction combined with translucency, or partial scattering through the upper layers. If the outer crust of 3i Atlas is thinner in certain regions or composed of a semi-translucent, radiation-hardened material, sunlight could penetrate slightly into the surface, scatter internally, and re-emerge on the opposite side as a weak glow. Some icy bodies exhibit internal scattering when the ice is clean and crystalline. However, 3i Atlas does not behave like an icy body. Its silence against solar heating and its resistance to sublimation suggest a consolidated, dense crust, not the porous, semi-transparent structure needed for internal scattering. A fourth hypothesis involves reflected solar-wind interaction. If the surface contains conductive minerals or fused silicates, it may glow faintly under charged particle bombardment. Certain materials luminesce when hit by solar wind electrons, yet this effect is usually seen only in laboratory conditions or in large-scale auroral phenomena. Seeing it on a compact interstellar body without accompanying plasma signatures would be unprecedented. Still, the compression wave shadow observed earlier indicates an unusual interaction between 3i Atlas and the solar wind, so a faint particle-induced glow cannot be ruled out. The most compelling aspect of the dim-side illumination mystery is its stability. It does not flicker, it does not shift, it does not behave like a transient phenomenon. It remains a thin, consistent crescent hugging the night-side limb. This consistency suggests that whatever mechanism produces it is structural, not event-driven. It is part of the object's surface behavior, not a temporary effect of changing geometry. For scientists, the dim-side glow becomes an important clue. It suggests that 3i Atlas may possess a layered surface with unusual optical properties, capable of absorbing, storing, and re-emitting light in ways not seen in typical comet nuclei. It reinforces the idea of a hardened, interstellar processed crust, dense, consolidated, possibly fused, that interacts with light differently from porous, volatile surfaces found in our solar system. In essence, the night-side glow hints at an object shaped by long exposure to cosmic radiation, micrometeoroid impacts, and deep space conditions. It glows softly in darkness not because it is active, but because it is built differently. And that difference, quietly illuminated in Tianwen-1's images, challenges everything scientists expected to observe from this silent visitor passing through our sun's domain. When Tianwen-1 observed 3i Atlas on the morning of November 12, one of the most revealing datasets came from its infrared sensors. These instruments, though not as advanced as those on board dedicated observatories, are sensitive enough to detect thermal emissions from small bodies passing through the inner solar system. In comets, infrared readings are often the most informative clues available. They expose sublimation, reveal dust content, highlight volatile chemistry, and map temperature gradients that visible light cannot show. But in the case of 3i Atlas, the infrared data delivered an unexpected outcome. Silence, a near-complete absence of thermal signatures that any normal comet or warmed interstellar body should display. This phenomenon, now termed the infrared silence, became one of the clearest indicators that 3i Atlas is not behaving like an ordinary comet. In typical cases, infrared sensors detect heat emitted from the nucleus and the surrounding dust cloud. Even a faint coma produces a measurable glow as warm dust grains radiate absorbed sunlight. Sublimating gas, especially carbon dioxide and carbon monoxide, leaves strong infrared fingerprints. None of these appeared in Tianwen-1's data. The spacecraft recorded only a weak uniform emission across the nucleus, without the characteristic peaks or gradients that indicate volatile activity. To understand why this is so significant, we must consider how infrared signatures normally behave. When a comet warms near the Sun, the temperature difference between sunlit and dark regions becomes pronounced. Ices vaporize, releasing gas that absorbs sunlight and re-emits heat. Dust grains lifted by sublimation glow in infrared wavelengths. Even dormant or low-activity comets show patches of elevated thermal emission. Infrared silence is extremely rare. It usually means one of two things. Either the body is extremely cold and inert, or its surface is sealed by a material that prevents heat from escaping in the usual way. 3I Atlas does not fit neatly into either category. It is too close to the Sun to be cold, yet too silent to be volatile. This paradox lies at the center of the infrared anomaly. One proposed explanation is that the object is coated with a radiation-hardened crust. Interstellar travel exposes bodies to cosmic rays for millions of years, which can bake organic compounds into a thick, insulating layer. Such a crust could trap heat internally, preventing the typical infrared glow from escaping. But a sealed crust comes with its own contradictions. If heat were fully trapped beneath the surface, subsurface ices would build internal pressure, eventually cracking the crust or blowing out gas vents. Tianwen-1 observed neither. The surface remained intact without fractures or outgassing events. The crust would need to be not just insulating, but structurally strong, far stronger than the crust seen on known comets. Another hypothesis suggests that the object's material composition includes minerals with low emissivity. Certain metals, silicates, and fused carbon compounds emit significantly less infrared radiation than porous ice or dust. If 3I Atlas possesses a mineral-rich surface, a possibility hinted at by its reflectivity spikes and unexpected color ratio, its thermal emission would be suppressed. This could explain the infrared silence without requiring subsurface activity. The surface would simply radiate heat inefficiently. Such material properties have been documented in meteorites and some asteroids, but rarely in compact bodies exhibiting non-gravitational acceleration like 3I Atlas. A third explanation proposes that heat is being redistributed unusually efficiently across the surface. The thermal contrast anomaly detected earlier in the data suggests that 3I Atlas may possess exceptional thermal conductivity. If the surface spreads absorbed energy evenly, the temperature gradient from day to night would be very small. A shallow gradient produces weaker infrared emission. This could account for the uniform, faint infrared signal without invoking exotic materials. But this explanation conflicts with the presence of a persistent warm strip on the surface. A body with high thermal conductivity should not maintain narrow, localized hotspots. The infrared silence also challenges the idea of sublimation-driven motion. Earth and Mars-based Doppler measurements confirmed that 3I Atlas is accelerating slightly in ways inconsistent with pure gravity. Usually such motion comes from outgassing, but sublimation would produce strong infrared signatures. The absence of those signatures implies that the force acting on the object is either invisible to thermal sensors or not related to gas at all. A final possibility involves surface microstructure. If the crust is highly compacted, fused or vitrified, it may reflect sunlight efficiently while also trapping heat in a way that limits external emission. This scenario aligns with the dim-side illumination mystery and the harsh light survival test. A surface that interacts with light and heat in unconventional ways could naturally produce infrared silence. The broader implication is clear. 3I Atlas is neither an active comet nor an inert rock. It absorbs heat without responding like ice. It warms without glowing. It accelerates without releasing gas. The infrared silence becomes a physical signature of a body processed by deep time and interstellar forces, an object whose thermal behavior falls outside the categories defined by our solar system. And in that silence lies one of the strongest clues yet that 3I Atlas is unlike anything astronomers have studied before.